All right, we were working last time in section 3.1. We had done a couple of numeration systems so far. Does anybody remember which ones we've done? Don't look at your notes. Just tell me if you remember. And if you don't, it's okay. But does anybody remember? Egyptian was one. Mayan, which is one we're in the middle of, and there's one more. Babylonian, very good. So you guys do remember, and I don't think anybody probably looked at it while you were gone, so that's pretty good. 2 days away, and you remembered that. That's good. All right, we're going to jump back in with the Mayans, because that's the one we were currently working on when we left, and just talk real quick about those symbols that they had. So they had this weird system, at least it's weird in the sense that it didn't happen in the other ones where they worked vertically from the bottom up. That's a little different. They did have a placeholder of 0, and we talked about how that's a good thing, because the Babylonians didn't have that, and it caused some problems. But they don't always have things just absolutely perfect. We did encounter a few weird things in their system. The other two symbols they had were one that looks like a dot, and that's worth 1, and a horizontal line, which is worth 5. And always the dots are written above the bars. We talked about the fact that if we were looking at this example right here, we're going to draw the line for the break in place value in as few places as we know would have to happen. So that's where that blue line is drawn. So is it possible there's more blue lines to separate place values? Well, yes. I mean, that's part of the problem with their system. But when we're interpreting a number in their system, we're going to attempt to draw as few blue lines as possible. Okay? So that's where we had left off. And we were working, I think, on this one right here, where we had a number in our system, and we're going to turn it into a number in their system. Does that sound good? All right. We did an example of this with Babylonians last time. Of course, their system was different, but the process is still the same. So where we left off last time is having written down all their base place values. Okay, so the place value in their base system, they have the 1's place, the 20's place, the 360's place, the 7200's place, and then we got 144,000, which was too many. And we got those, if you'll remember, too, by multiplying by, where was it? It's over here. Multiplying over here on the right-hand side by powers of 20. And then there's this one awkward, really weird, like 18 in the middle of one of them, and it had to do with their calendar system. Okay, that's why that's there. So that's where this list of numbers kind of comes from. All right, so do you guys remember how we did what I called it a division scaffolding? Does that ring a bell from last time? Okay, great. The number that you're getting right here, that you're given right here rather, is the number that you're going to be using with the division. And it goes under what sort of looks like a top hat. And the number that's going to go on the left-hand side in front is simply the largest place value number that's still smaller than the number we're given. So in our case, that's the 7200. Okay, is everybody good so far? Okay, and then here's where you get to use your calculators. They're very handy. What I want to know is how many times this goes in evenly. So like if you do it in your calculator, tell me the whole number of times you get out of your calculator. 8. Okay. That's how many whole times it comes in, so it goes in. So you're going to take 8 and you're going to multiply it by the 7200. $57600. Awesome. What are you going to do next? Subtract, right. Very good. Okay, so let's subtract what we have. So 58,532 minus 57,600. 132. We don't have very much. 932. We still don't have very much left compared to where we started, right? All right. The next thing we do is we use the next place value, even if it's too big. Now, in this case, it's not. Oh, I wrote it wrong. I'm sorry. Thank you. I was so excited to move on. Man. Okay. We're going to use the next place value, even if it were too big. In this case, it's not. But even if it were, we would still write the next place value on the bracket on the outside. And we're going to divide. So how many times, whole times, does 360 go into 932? Twice. Exactly. So then what's 360 times 2? 720. Great. And we're going to subtract. So what is 932 minus 720? 212. Okay, what's going to go on the outside now? Not 10, 20. Okay, maybe I just heard wrong. All right, so yeah, we're going to put the next place value, which is a 20, on the outside. How many times will 20 go into 212? That is 10 times. Is that the 10 that you were telling me, Kaylee? Gotcha. I'm with you now. All right, and then what is 20 times 10? 200. leaving me with 12. And what is my last division by? 1, and that's always going to be my last division, dividing by 1. How many times does 1 go into 12? 12 times. And if I multiply, of course, I get a 0 here at the end, and I'm done. I need that 0 at the end. I need my last division to be by the number 1. These numbers over here, get the one at the top, these ones right here are what are going to inform me as to how to write their number. Now, the answer is not 8, 2, 10, 12, right? But we're going to use those to make their marks, their symbols with that. So how do I get the number 8 in Mayan? A line. What else? 3 dots. Where do the dots go? On top. Fabulous. So that's my 8. How do I get a 2? 2 dots. Where are the 2 dots going to go from where I currently am? Below it, right. 2 dots underneath. So I'm going from I'm writing it from top down just because I've got my numbers already listed here. We could write it from bottom up. That'd be okay. The next number is a 10. How do I write a 10? 2 lines. And do you see something awkward that just happened? Yeah, now I can't distinguish between that third value that I had was the number 2 and the second value was the number 10. That's sort of not good, right? Okay. And then my last one's a 12. How do I get the 12? 2 lines and 2 dots, and the dots go on top of the lines. So there is, of course, a problem with this in general, is that this actually looks an awful lot like what I would have if I had 8 times something plus another 12 times something and 12 times that something. I shouldn't be saying something. That's not so good. We're gonna fill in the somethings I keep saying. 12 times 1 at the end. So if I were actually thinking about this, like if I were given this display and I worked it out, I'm probably not going to think this number was 58,532. I'm much more likely to draw my lines in right here. That's not a good line. Let's try again. I'll use blue. Right here, that gives me 12 in the middle and 12 on the bottom and 8 on the top. That's my 8, 12, and 12 that I wrote below. So that would give me 8 times 360, 12 times 20, and 12 times 1. That's where the natural breaks for sure have to happen, right? They have to happen there. There's nothing that tells me that they should happen anywhere else. So I'm quite likely to think that this is actually the value that this is representing, and this value is actually 3,252 if my notes are correct. And I don't know about you, but if somebody owed me $58,000 and they only paid me $3,000 because my number system was ambiguous, that would not be happy times, right? Yeah, that wouldn't be good. I mean, so obviously there's an inherent problem with this. There's this inability to distinguish place value in certain situations. Not every situation, but in certain situations we have this problem occurring. Okay, so these are the Mayans. Any question before we leave the Mayans and move on to the Romans? All right, so this is probably the most likely system that you've used, that you've heard about, that you've worked with, and that you see used today. So before we get started too far, go ahead and write down the Roman numerals. You guys are all doing it anyway. Go ahead and write down the ones that are there. We'll put in the place value next to them, and then we're going to talk about them a little bit. So just jot down what's there first, and then we'll put the place values in. Or not the place value, the values in. All right, what fun. You know some of these. What's the first one's value? It's a number 1. You got it. This has the value 1. What about that V-looking symbol? 5, yeah. X? 10. And that's probably as far as you look in terms of like outlines, right? Outlines is somewhere you see these. Is probably as far as you go. Some of the other symbols are used in other places. Let's fill them in and we'll talk about other places we see them used. Does anybody know what L is? Close. It's 50. What about C? That's actually 100, yeah. D? Good guess. It is. It's 500. What do you think M might be? Look at the pattern. Do you see a pattern? It's 1,000. Yeah. It is 1,000. All right, so two things. First, let me say briefly, you don't need to memorize any of these base systems, okay? And when you get to your test, you don't need to write them on your card. Because when I do the test that has this material on it, in fact, I even have them that I just hang on to them, I give you the sheet that has all the systems and their values on it. This is not my expectation for you to memorize these or even to use your card space for them, okay? So that's good news, right? Yeah. All right, so I'll have that for you. Okay, now let's go back to Roman specifically. Where, besides outlines, maybe, have you seen Roman numerals used? There's lots of options. Somebody tell me one. Clocks, that's a good example. What else? Huh?
Football.
Say it louder, yeah. Football. You guys seen that? So think about like, give me an example. The Super Bowl. Thank you. That's what I was trying to come up with. Super Bowl. They'll put the Super Bowl number down like that. What else? They discontinued that? I didn't know that. What a bum. That was a fun place to see it. There's a couple others that I've seen it in. Along the lines with Super Bowl, the Olympics does it as well. You'll see it with the Olympics. Another thing is if you happen to travel, and this doesn't happen in Oklahoma because Oklahoma is a very young state by comparison, if you happen to travel over in the eastern part of the United States, especially the northeastern part, so think, like Washington, D.C., hold historical kind of things, a lot of times you'll see dates on buildings put in Roman numerals. So you do see them in other places that are sort of outside the realm of what happens sort of in literature. We see them in literature a lot, right, with outlines or sometimes the title, the section number or a chapter number of a book. They'll use Roman numerals sometimes. Now, there's a couple of interesting properties aside from the number systems. Inherent in what we sort of see right here is the problem of what happens if the number is bigger than 1,000, right? And there's also this issue of, well, what about the other numbers? What do I do for the numbers 2, 3, 4, 8, 7, 8, 9, those kinds of, 6, 7, 8, 9. I mean, how do I sort of compose these in a way that actually makes sense? So they have two features that are different than anybody else's systems for how to deal with that. So the first thing we're going to talk about is the second issue I actually brought up was about the numbers. They have a property that I'm going to call it a subtraction property. So to avoid repeating symbols more than 3 times, they will use a smaller value in front of a larger value. So most of the time they have the smaller value after the larger value. Kind of like with the Mayans, they put the dots over the bars. Okay? So in their system, in order to avoid writing something 4 times, like the number 40, we don't write 4 X's for the number 40. Okay? So what do? Well, anytime they have a number 4 or a number 9, it's only those 2 numbers. So you can't sort of apply this in other situations. Okay? Only for 4s and 9s. They use a value before it to indicate subtraction. So here's the example I have for the number 90. The number 90 is awfully close to the number 100, and we have a symbol for the number 100. What is that symbol? It's C. So what they would do is they would write the C down, and then they would use a symbol in front of it to indicate that we want to take 10 away. So what is the symbol for the number 10? X. So the fact that the X is happening before the C indicates subtraction. Okay, I didn't make it up, so you don't have to like it, and I'm comfortable with you not liking it too. It's okay. But that's how they used it. They would have used the X in front of the C. Now this is important to realize that this only works with one place value smaller. So take a look back over here. If I'm talking about the number 100, and I'm using the C, of course, for it, I can't put just anything in front of it and use a subtraction property. Like, for instance, not that it would make any sense to do it, but I can't simply put an L in front of the C and say, oh, that's 50 and 100, and since the 50 comes before the 100, it means 50 as well, right? Subtraction. No, that's not appropriate, okay? The only thing that I can put in front of a C is an X. That's my only option. L can come before a C, but nothing else. It has to be one place, or one, I don't want to say place value exactly, but one digit less, all right? So if I had the number 100, it's a 3-digit number, and this is the nearest value smaller that would make something work, okay, the 10 here. So in other words, I can't put an L in front of a C, but likewise, I can't put a V in front of a C or an I in front of a C. Like, let me tell you what, I would love to write 99 IC. That'd be great, but they don't do that. Okay? So when they get to the number 99, they're going to treat 99 like 90 plus 9. They're going to deal with it as though they're 2 separate parts of the problem. So we know how to write 90 because I just did that one, right? And you guys just did that one as well. It's XC. How would I write 9? Well, 9's awfully close to 10. 10 is the value. What X, right? So how would I have the X and take away something to make it 9? I need a 1 or an I beforehand. So this is understood to be 90, and this is understood to be 9. So it's 99. So there is no IC. That does not work. And again, it's not my choice. It's just really, like, we're doing it historically the way they really did it. Okay? And the same is true for 4s. So if we had 40, we would write X and then L, because L's worth 50, and we'd want to take 10 away. Okay? Again, so for 49, I can't do a 1 before a 50. That doesn't work. It's not how they did it. So we're going to treat it the way they did it. So we'll have some more practice on this. This is one of their properties. And I know you're a little bit familiar with this because you've seen this in literature. You've seen them write the number 9, for instance, as IX. So you've seen this before. Take a look at the next one, though. This one actually deals with the issue of what happens if my values are larger. And that is larger than the number, really, it's larger than the number 3,000. Okay? So if I had 1,000, what was that symbol for 1,000? It's M. So what would I do if I had 3,000? It's not a trick question, I promise. What would I do for 3,000? 3 M's, exactly. Okay? So we're going to repeat the digits, but we only repeat the digits 3 times. So inherently in this comes a problem of what happens if it's 4,000. That's a problem. I don't have a way to do this yet that allows me to make something bigger than 3,000. I mean, and we can have 3,492. That's not the problem. But I mean the 3 of the 4 in the thousands place is the problem. So they have something that they deal with, and it's actually a multiplication property. So what they do is they place a bar on top of the numeral if they want it to be multiplied by 1,000, and they place 2 bars on top of it if they want it to be multiplied by 1,000,000. Okay? So not to confuse things, but here's my example. I'll go back to the 4,000 in a minute, but I used 9,000 on this one below. Obviously, 9,000, based on what we've had prior to right now, means that I would somehow have to write 9 M's because I don't have any other choices. I'm running out of digits, right? Well, what we're going to do is we're going to treat the 9 as though it's just 9. How do I write a 9? IX. And then the way I get that 9 to mean 9,000 is that I write a bar on top of it. The bar on the top of it means times 1,000. So what would it be if I had 2 bars on top of it according to what I wrote down a moment ago? That's 9 million. All right, so let's think back about that 4,000 because I just brought it up out of middle of nowhere up here. What would I do for 4,000? Right, so the number 4 is IV, and then the way we get it to be 1,000, like Amanda said, is the 1 bar on the top of it. Okay? Now, it isn't appropriate to do that with 3,000 or 2,000 or 1,000 because we have symbols for those. All right, so we're not trying to recreate new ways of writing the things we already can write. That's not the point. Okay? So if you told me that 3,000 is 3 I's with a line on the top, that's not what they would have done. That's incorrect. Okay, but anything that's 4,000 or bigger, we have the need for doing something different, and this is the method we'll deal with it. Okay, is everybody good? Do you give a couple examples of these now? Okay, let's take a look at an example. We've got MCMX. And the first thing we're going to do is we're going to do the same things we were doing last time. What comes before, what comes after. And as with all the other ones, looking at before and after means looking at the smallest place value here. So what value, and I mean in their system, what numeral do they use in their smallest place value here? An X, okay? So really the focus is on the very end of this value, this X, and we know that X is the number 10. Okay, so one of these two questions, and this has happened every time I've done an example like this, one of these two, A or B, is easy, and the other one's a little bit more challenging. Which one of these two is easy? The one that comes before or the one that comes after? After is easier on this one. What comes after 10? 11. How do you increase this by 1? You just add a 1 on the end. So part B is the easier of the options here. Not that part A is terribly difficult on this one, but it's a little bit harder. So this is MCMX, and then you just add a 1 on the end. This would be having the number 11 on the end, right? Everything else before it stayed the same. But if I want the number before, the x actually has to change in some other fashion. Now this one's not a terribly difficult change. It was messier in the other systems when we did that, right? Like we had to change a bar into dots, or we had to change a less than sign into triangles or something like that. This one's not too bad. How do I change that x at the end to represent 1 less? I put an I in front of it on this one, right? Oops. MIX. So that gives me a 9 at the end instead of a 10 at the end. So that's the number beforehand. All right, we're going to figure out what in the world is this numeral in the Hindu-Arabic numeration system, like for us. Okay, so as we're taking a look at this, and I mean the original numeral that we were given, MCMX, we actually, oh, I wrote it wrong even, didn't I? Oh, goodness. All right, let's try that again. We need to identify where we see smaller values in front of larger values. We need to identify that. Do you see any locations where a smaller value is in front of a larger one? The C in front of the M. The C, and sometimes it's helpful to simply write out what each of these individual values are. C is 100, right? And the M's are 1,000, and then the X is 100. So it is that C, M in the middle where I have a smaller value in front of a larger one. That's the only location then where I'm going to be using subtraction, because the smaller is before the larger. So the first value, that's 1,000, will simply be part of my answer, 1,000. The CM means I've got a smaller in front of a larger, and I subtract. So what value is C followed by M? That's 900, because it should be 1,000 minus 100. And then the value at the end, oh, I wrote something down wrong. No wonder you guys are staring at me like I'm weird. How about this should be a 10? I got a little carried away with my zeros, I guess. Does that look better? It looks better to me. All right, then we have the X at the end, and the X at the end would be the value 10. So what is this numeral in Hindu-Arabic? 1,910, which you definitely could see on a building, actually, as a date. So that's a reasonable kind of number to see in real life. All right, we're going to go the other direction. This is a fun one because I got some bigger value going on here. We've got 1,492. I'm sorry, 1,492,019. Let's try that. And we're going to write this in Roman numerals. So first of all, this number is a quite large number, so we're going to have some bar stuff going on, right? Okay. All right, so let's identify where we see place value breaks. And it's really nice because it happens where we have our commas. So basically, before that value, I see something that I'm going to have something with the millions place. In between my two commas, I see something in the thousands place. And then after the commas, I see something that I can deal with without any bars on top. It's simply the number 19. So we're going to do this in 3 separate chunks. We're going to ignore the fact that they're millions and thousands, and we'll put the bars on at the end. So the first number is a 1. How do I write a 1 in Roman numerals? It's an I. Put the bars on top or on bottom, it doesn't matter, but this is what you would do. How do I write the 492? Well, let's start with 400. How do I write 400? L's are 50s. So what are you going to do to get 500? I don't think we want C, D. So why would C, D work? C is 100 and D is 500. So if I put the 100 before the 500, I get 400, right? Very good. We'll write all our answer out when I'm done. This is sort of scratch work in the process. Okay, that's my 400. How do I get 90? So I need X, which is 10, and I need C, which is 100, right? 90 is almost 100. That's where the C is coming from, but it's 10 less. So I've got X followed by C. You guys are doing great. How do I get the 2? 2 I's. Awesome. Okay, and I'm sort of giving this natural sort of break here and here. What happens the 9? Okay, let's break it apart. Yeah, so you have to start with the 1, right? I can't do 19 directly. I need to start with the 1 in the tens place. So how do I get the 10 part of 19? That's x. Good. Whoops, and for some reason I decided to change my color of my pen. I don't know why I did that. How about the 9 then? That's a subtraction property, right? 4s and 9s. That's the IV, or IX, excuse me, that we've seen before. Now, those yellow bars are sort of breaking apart the fact that we've got the millions place, the thousands place in the middle, and then the normal single digits that we have on the end. So here's what they do. They take the first one, and they draw 2 lines on top of it. Okay? They take the second one, C, D, X, C, I, and they're going to draw 1 line on top of it, because that's the thousands place. And then they're going to do X, I, yeah, I said it right, X, I, X. For the 19 at the end. And all of this combined would be the number 1,492,019. And it really does break apart by place value. Now there is one other option on how to think about this. You want to look at one other thing? So this is correct. There's one other thing that we could do. The one other thing that we could do is that we could take away this place value right here. And we could write down what this would look like as the number 1,492. How would that change if we did that? What's 1,000? It's an M. So instead of this piece right here, I could have M, and then everything else is the same, C, D, X, C, I, X, I, X. And this could have 1 line on top of it. That would be an alternate way of writing this based on their system. Either of those would be correct. Okay? So what they're doing is treating that number as though it's 1,492 and doing it from that point and then writing a 1,000 bar on top of that. Either of those would be acceptable. All right, is everybody okay with that? Okay, let's move into a little bit different direction. We're going to talk about some manipulatives that I'm going to guess that you've probably seen these used before in a classroom. They're very common. These are called base 10 blocks. Has anybody seen base 10 blocks used? I so should have brought my base 10 blocks. I'll bring them next time so that you can see them. They're not very exciting per se, but they really do give credence for how our number system works. So there are 4 types of base 10 blocks. The first one is called a unit block, and a unit looks like a little square. And because they're 3-dimensional objects, they actually look like, they almost look like a little bitty cube, actually, just because they've got some depth to them. You could do it on regular paper, and then it wouldn't matter. But they look like a little square. A long actually looks like 10 of those little squares all stuck together. Okay? So because it's base 10, this is 10 units. A flat, any guesses as to what that might look like? Okay, if not.
100.
Yeah, it's going to be 100. It actually looks like a giant square. I'll try to make mine look squarish. And it really is 10 units here and 10 units here. Or you can think of it as being 10 longs. So if you take a unit and you stick 10 units together, you get a long. And if you take a long and you stick 10 longs together, you get a flat. So your image, I'm not drawing them in, but I'll draw in a few just to give you an image. Here's a long, and here's a long, and here's a long, and they're exactly the same size by definition. I didn't draw them well, obviously. But pretend for the moment that they all look alike. And there's 10 of them across. Okay, so there's 100 little bitty squares basically in there. Any guess what might do for a block? What's that?
1,000.
It is 1,000. Very good. And it looks like a 3-dimensional shape. And that wasn't perfect, but it was actually fairly decent. So this is actually 1,000 blocks, 1,000 units rather. It's a 10 by 10 by 10. Okay. 10 wide, 10 long, 10 tall. 1,000 units. Okay, so this is what we do with base 10. What would happen if we were working in base 8? In base 8, how much would a unit be worth? Well, it's still worth 1. A unit is always worth 1. Doesn't matter what base I'm in, a unit's worth 1. But things get different when we move on to the longer pieces, like a long. If base 10 has 10 values or 10 units in a long, what do you think happens in base 8? Yeah, there's 8. So in base 8, I just stick 8 of these units together to get a long. What about a flat? Good try. 64. So Amanda, where are you getting 64? Right. So if you come back over here, the reason it's 100 is because we have 10 long and 10 wide, right? 10 by 10. So if we're dealing with base 8, we'd have 8 by 8, which would give me 64. What would I do for a block? Like that? Mm-hmm. It'd be 8 by 8 by 8, right? So 8 long, 8 tall, 8 wide. What does that give me? What's 8 times 8 times 8? 512. So the base system that we're in ends up being powers of that base. Ours is powers of 10 because we use base 10. But I talked about last time, if God had made us and we didn't have thumbs, we'd probably be working in base 8. Have you ever seen any other base systems? I'm not going to say have you ever. Can you think of any? You've seen them. There are several other base systems that are used in our society today. Any thoughts? I'll give you an obscure one first. Everybody's probably got a smartphone. Or maybe yours is dumb, like mine right now. It's actually a smartphone. It's just acting dumb. Most of us have phones. Most of us have a calculator. I see many calculators out on your desk. All of you have been using computers at one point or another here on campus, right? Programming inside of computers, and phones and calculators these days are computers, occurs in binary. Do you know what binary is? It's base 2. Uses zeros and ones. They use base 2 for computer programming. The other thing they'll sometimes use in computer programming is something called hexadecimal. That's a fun word. Impress your friends this weekend with that word, hexadecimal. It's base 16. Okay, so you're going, okay, great, but I'm not a computer person, at least not in the sense of programming something, so why do I care? There's something else in this very room that you've used this for, and you use it for every single day. Over there on the wall, what is it?
Clock.
It's a clock. Does our clock work in base 10? It does not. If you think about seconds and minutes, you're actually working in base, what? 60. 60 seconds in 1 minute, 60 minutes in 1 hour, right? That's base 60. You can have an example of that in your homework or group work. I don't remember which one. And then once we get to hours, we're actually working in either base 12 or base 24 if we're using military time, right? So we use those kinds of things every day. We're going to do some examples of some other number systems. And base 8 is where we're going to start. So we're going to take a look a little bit with what happens in base 8. So this number 237 with the little subscript 8, we're going to see the little subscripts written to tell us which base we're in. That's what's going to tell us. Please use the words instead of numbers, because if you use the numbers, undoubtedly something's going to end up looking larger than you meant it to look like, and then I'm going to be wondering what that number means. If you write the word down, I don't have to wonder. We're all on the same page. All right, so if you take a look at what this is written as, this is the units place. There's 7. This is the eighths place, the longs place, and there's 3. And this one is the 8 squared or 64s place, which is the flat. Okay? So anytime we're dealing with changing in and out of bases, we can think about this idea of longs and units and flats. So how much, quote unquote, is a flat worth in base 8? What do we write down? 64. So this is saying I have 2 flats, and they're each worth 64, so I have 2 64s. Then I've got this number 3. How much is the long worth in base 8? It's worth 8. So this is 3 eighths. And then I've got 7, and that's my units place. How much is the unit worth? 1. And it always ends with the 1 in the units place. So you're going to grab your calculator out, and you can actually take 2 times 64 times plus 3 times 8 plus 7. And we can turn this into the value that we would have of these units, how many units this would actually be. Did you get an answer? 159. Do I have a second on that? Fabulous. 2, 3, 4. I hear several people saying that. So this is 159. This question in part B, it was posed in terms of these manipulatives. How many unit blocks would this be if I individually counted them? This is the same as asking, what in the world is 237 base 8 in base 10? Or in Hindu Arabic, or however you phrase it. But in other words, turning it into how we look at numbers and our worldview of numbers at this point. Okay? So simply put, that's what this is doing. So let's actually talk a little bit about a couple other systems, and then we're going to work inside of them a little bit. What is base 3? Well, in base 10, we had how many numerals? Do you remember? We talked about this last time. How many numerals we had? 10. So in base 10, we have 10 numerals, 0, 1, 2, 3, 4, all the way up to 9. There's 10 different numerals in base 10. So how many numerals do you think there's probably going to be in base 3? 3. All right, and the numerals always start at 0. Okay? And then we're going to go 1 and 2. And that's 3 numerals, so I'm done. So what's that mean? Well, number 1, it means there's no 3 in base 3. Just like there's no 10 in base 10 as a single numeral. Right? We have something that we call a 10, that's fine, but it's not 1 digit, wide or something like that. So there's not a 3 in base 3. So what would happen in base, what does happen in base 10 once we run out of our numerals 9? What do we have to do? We have to put them together, right? We have to use 2 numerals to represent the next number, correct? And the next number in base 10 after 9 is the value that we put 1, 0 with the 1 and the 0 right beside each other. And that's actually the same thing that's going to happen here as well. We're going to combine them with a 1, and so we're going to get 1, 0, and then 1, 1, and then 1, 2, and then I'm out of numerals again. There is no 1, 3. So what do you suppose comes after 1, 2? 2, 0, and then 2, 1, and then 2, 2. I'm going to go 1 bigger. I'm out of numerals again. What comes next? I need 3 digits, right? And it's going to look like 1, 0, 0. Notice the language I'm using. I did not say 100, right? When I say the number 100, that the phrase, the word 100, actually puts me back into base 10. I'm not in base 10. So I'm going to say the individual numerals one at a time. 1, 0, 0. That's how I'm going to use the language, okay? All right, let's take a look then at base 7. How many numerals are there going to be in base 7? 7. We're going to start at 0, and we're going to go up to what? 6. Good. What would come after 6? 1, 0. And then 1, 1, until I get to what? 1, 6. And then I run out of numerals, and then I change this into 2, 0, and we'll pause there. The process continues, right? I could keep writing numerals all day if I wanted to. I have to stop every time I get to a 6 in that place and change it up to the next number of place values, or the next value larger than that in that place value system. 12's weird. 12 is weird. Why? I need more than I've got, right? All the other 2 that I've talked about, and even base 8 before, I needed fewer digits, so I just stopped short of using the rest of the digits I have. So I got to figure out what I'm going to do when I need extra digits, basically. All right, so here's what I'm going to do. I've got from 0 all the way up to 9. That's cool. But I need more digits. This is only 10 digits, right? How many more should I have? 2. So I'm going to be consistent with what your book does, even though it's not my favorite way to do it, okay? For 10, they use T. For 11, they use E. And if we needed a 12, like if we were in a bigger place system for 12, which occasionally the book will do, they'll use a W. They don't actually ask you to go any higher than that. This is not my favorite because they're using letters that start to repeat themselves. What if I needed a 14, a 15? Those are both Fs. What am I going to do then? Like, that's not cool. There's another textbook that I've used with this before, and they use the letters of the alphabet in order, A, B, C, D. I think that's better. But we're going to go with what the book's using right here. So T is for 10, E is for 11. But once I get to the E11, I run out of digits, right? This is 12 digits. So what comes after E? 1, 0. 1, 1, all the way up to 1, 9. What would be after 1, 9? It's going to feel awkward to say it. Say it anyway. 1, T. And then 1, E. And then I'd have 2, 0. And we'd keep going. Weird, right? It is. It is weird. I agree. However, working in these different base systems is much like working in our different numeration systems, Mayans, Babylonians, Egyptians, and so forth. We can use their system in much the same way. We can use these different bases in much the same way. Before I actually start in, I always have students sort of feeling like, I'm not going to teach this in the schools, and that's a true statement. You're probably not. If you teach the gifted kids, you actually might. That's a possibility. Like in one of the gifted classrooms or something like that, sometimes they'll do stuff with base addition there. So I always have students feel like, what's the point? There's a couple of things here. One of the points is that we feel very comfortable working in our base 10 system, right? You guys feel very comfortable adding and subtracting in base 10. You've been doing it for a long time, right? Well, the kids in your first grade classrooms, second grade classrooms for multiplication maybe and things like that, they don't feel quite so comfortable adding, subtracting, multiplying, and dividing because it's new to them. So part of what you're doing in this is really giving yourself a firm foundation of what it really means inside of base 10 because you're doing it inside of some other base. So it's going to make you feel a little bit uncomfortable to hopefully help you identify with your students a little bit better too. So that's kind of where this is coming from, okay? So let's take a look at what this is. We've got different bases. This first one starts out with 1, 4, base 5. And it'll help us if we think about those base 10 blocks. But now we're going to think of them as base 5 blocks. So in base 5, we still have 2 place values here, right? The 1 is in what place value? What is it worth? It's worth what? It's a long. You're right. It's a long, and it's worth 5. Exactly. So in this place value system, it is worth powers of 5. It's power 5. And the 4 is in the units place, and units are always worth 1. So taking our knowledge of base 10, well, the 1 in that place is not 1. It's actually 1, 5. So if you can think about this actually like dollar bills, I have 4 $1 bills and I have 1 $5 bill. Right? So how many dollars do I have? 9. I have 1 $5 bill, 4 $1 bills. This is actually the number 9. It's worth 9 anyway. We can do the same thing with this weird T00 business. So as we look at this, this is base 12, which means my longs, my flats, my cubes, all of that kind of stuff actually have powers of 12, right? So the 1's place is always the place to the right. The long is the next one, and that's a place value worth what in base 12? It's 12, right? I'm in base 12, so this is worth 12. The next one should be worth 12 squared, and then it'd be 12 cubed, and then 12 to the 4th. It's always powers of whatever the base is. So I actually have, I'm going to write this out a little bit differently, the 1's place, the 12's place, and the 12 squared's place, just to give me some more space. I have 0 1's and 0 12's. How many 12 squareds do I have? 10. T is 10, exactly. So I'm going to write the numeral that we use for that value there to help me with my multiplication. 10 in the 12 squareds place. What do you think I'm going to do with those numbers now? Everything else is zeros. I'm going to multiply. I'm going to take each value, and I'll write it out this way even though they are zeros. And I'm going to multiply the value in that place times the value of that place. So the value in the place is the 10, 0, 0. The values of the placeholders themselves are 12 squared, 12, and 1. It's a multiplication exercise. Okay, what's 12 squared? You guys know that, right? 144. So what is 144 times 10? 1,000. Oops, I left off a 4, didn't I? 1,440. And the other 2's are zeros, right? because I multiplied by 0. So this is actually the number in base 10. Occasionally I have students ask, how do I know which base I'm in? And it's the subscript. So if you don't have a subscript like my two answers here, then I'm automatically in base 10. If it bothers you, or if you're concerned about being thorough, or you're concerned that you might forget it if you're in a different base, and you want to always write the actual subscript like the 10 down here, you can do that. That's okay. But it's not necessary. All right, we're going to go the other direction. We're going to take a look at what we do to take whatever base into base 10, because this is what we actually did in the last problem. We're going to put the numerals in expanded form. So expanded form, which we worked at before, means taking the value, like we did over here, the 10, and multiplying it by the 12 squared. That's the expanded form. And we did it back in, I don't even remember which section it was now, but something back in chapter 2 when we were looking at stuff. We were writing the value times the 10 squared, or times 100, right? 10 squared to 100. So we're going to do this sort of thing, and that's what this piece right here is telling us that we're doing. So we're going to put them in expanded form, and then after we put them in expanded form, we're going to multiply the expanded form out. And that's exactly what we did on this last problem. After we wrote it as 10 times 12 squared, we actually multiplied out 10 times 12 squared. So we're going to do some examples of that next. Oops, one more. So here are a couple other examples. We're taking, no wonder you guys are looking at me funny. I didn't follow my own directions. That's what happens when you don't read. I just did the different problem, didn't I? Okay. Think about what I want to do. Let's finish out this topic. I'll come back and I'll fix example 10 next time, okay? So let's continue on with example 11, part A and part B, and then I'll go back and fix number 10 this next time. We're looking at expanded form. So part A here is base 2, which means I've got powers of 2. And I've got 4 place values, right? So I've got the 1's place, the 2's place, and then I've got 2 squared and 2 cubed. And I've got a 1, a 0, and a 1 in the problem given. So the expanded form means that I'm going to have 1 times 2 cubed plus 0 times 2 squared plus 0 times 2 plus 1 times 1. And do you have to write out the 0 times? You don't have to. It doesn't hurt anything either. All right, what's 2 cubed? Good try. That's 2 squared. 8. Yeah, 2 cubed is 8. Of course, this middle values are both zeros. And at the end, I have 1 times 1, which is 1. So I actually get 9 here. Okay, so this is actually the numeral in our numeration system, base 10. This number T00, I already did that one, didn't I? That's the one I just did a minute ago, wasn't it? So I take, we'll just reiterate how we did that. 3 place values at the 1's place. I have a 12's place because I'm working in base 12, and then 12 squared. If I have any letters, I need to figure out what that letter means. The letter T means the number 10, and then of course the other ones are zeros. So then I have 10 times the 12 squared. I have the 0 times the 12, and the 0 times the 1, and of course we just did that a minute ago, and it was 1440. Okay, give me 1 second longer. Okay, that's not a true statement. I need like 1 minute longer. This problem didn't ask me to do what I did, right? It asked me to find the numeral preceding and succeeding. That is the number before and the number after one, okay? So as we're taking a look at this one, what we're actually doing is not what I did over here. That's why I just disappeared it. I made it go away. So we will talk next time when we come in about the preceding, succeeding values, and I'll start right there, okay?